Hello guys, still on our video on differential equations of first order and higher degree. We're going to be discussing about the case studies 3 and 4, just like I said in the previous video. So the third case study refers to equations solvable for x. So let's go through the solution steps for this method. Just like the equations solvable for y, you differentiate the given equation with respect to y. Then solve the equation that is obtained. And the goal of doing this is we are going to solve the equation to obtain p. So the third step is to eliminate p by substituting the value of p in the given equation. Then finally, the eliminant is the required solution. The eliminant just refers to the equation that we've obtained after substituting the new value for p into the differential equation. So let's take a question to explain this point. So the question says I should solve the differential equation y is equal to 2x dy dx plus y dy dx squared. So in order to solve this, we'll first substitute dy dx for p. So our new equation now becomes y is equal to 2px plus p squared. Sorry, plus yp squared. Or we can say p squared y. So 2px now becomes y minus yp squared. Now let's differentiate through by p. We have 2px divided by p is equal to y divided by p minus yp squared divided by p. So we have 2x is equal to y divided by p minus yp. We can now differentiate with respect to y. So in differentiating with respect to y, we have 2 dx dy will be equal to 1 over p minus y over p squared, the p dy. Then we have minus p plus y dp dy. Let me divide this place so we can continue. So we can go ahead to simplify this to become 2 divided by p is equal to 1 over p minus y divided by p squared dp dy minus p minus y dp dy. So recall that dy dx is equal to p. So we have that dx dy is equal to 1 over p, and that's why we had this here to be 2 over p. So we can now collect like terms. 2 over p minus 1 over p will be equal to minus y divided by p squared dp dy minus y dp dy. Sorry, there's one more p missing here, plus p. So we have 1 over p plus p is equal to minus y divided by p squared dp dy minus y dp dy. So simplifying this, we have 1 plus p squared divided by p is equal to dp dy, two brackets, minus y, two brackets, 1 plus 1 over p squared, and this becomes minus y multiplied by p squared plus 1 divided by p squared dp dy. On further simplification, can write this as 1 plus p squared divided by p is equal to minus y multiplied by p squared plus 1 divided by p squared dp dy. And we can see that 1 plus p squared is common to both sides, so you can divide both sides by 1 plus p squared. So on doing that, we now have that 1 is equal to minus y all over p squared. Sorry, 1 over p is equal to minus y divided by p squared dp dy, or multiply both sides by p. Then we have 1 to be equal to minus y divided by p dp dy. So this looks like a situation where we can use separation of variables. So we simplify this to become minus dy divided by y to be equal to divided by p. So we can then integrate both sides. On integrating both sides, we have minus integral of dy divided by y is equal to integral of dp divided by p. So we have that minus ln y is equal to ln p plus ln c. I'm using natural logarithm for the constants also just for the sake of simplification, and that's what we are going to see now. So we can write this as minus ln y plus ln c is equal to ln p. Let me make this capital letter since it's still going to be a constant. So we now have ln p plus ln y is equal to ln c. Then from our laws of logarithms, we have py to be equal to c, and p is equal to c divided by y. So the next step is to substitute this new value of p into the original differential equation. So recall that the original differential equation is 2px plus yp squared. And on substituting this, we now have y to be equal to 2 into bracket c over y multiplied by x plus y multiplied by c over y all squared. We can further simplify this to be equal to y is equal to 2cx divided by y plus c squared divided by y. So now on multiplying through by y, we have y squared is equal to 2cx plus c squared, and this can further be simplified as c into bracket 2x plus c. So therefore, the solution is y is equal to y squared is equal to c into bracket 2x plus c. And this concludes that question. So now, for the fourth case study, is a special case and very straightforward case known as the Clairaut equation. So any equation of the form y is equal to px plus a function in p is known as the Clairaut equation. And if you notice, this also looks like a form of equations solvable for y. So definitely we can follow the same steps as in the case of equations solvable for y. So we have y is equal to px plus a function in p. We know that p is equal to dy dx. So for equations solvable for y, we can differentiate both sides with respect to x. From differentiating with respect to x, we have dy dx will be equal to p plus x dp dx, plus using chain rule here or function of a function, we have the derivative of that function in p multiplied by the p dx. So we now have p to be equal to p plus x dp dx plus the first derivative of the function with respect to x multiplied by the p dx. So we can now eliminate p. So on eliminating p, we have x the p dx plus f prime p the p dx to be equal to 0. On factorizing both sides, we have the p dx multiplied by x plus the first derivative of the function with respect to x is equal to 0. This means the p dx is equal to 0. And just as we did that time, on integrating, you have p to be equal to c. You can now substitute this back to the original equation. Y is equal to px plus f of p. Now, p is equal to c. So we have y to be equal to cx plus f of c. And this is going to give us the solution of the differential equation, the required solution. So it means whenever we have functions of the form y is equal to px plus the function in p, by substituting p to be a constant, any arbitrary constant, we have our solution of the differential equation, and that's what is referred to as Clairaut's equation. So let's just take a question to see this concept. So we're required to solve p is equal to ln px minus y. The y dx has been made the subject of the formula in this case. So you can just go ahead to solve. Now, we know that if p is equal to ln px minus y, it means e raised to the power of p is equal to px minus y from our laws of logarithm. So you can further simplify this to be y is equal to px minus e raised to the power of p. And this looks like the same function as px plus the function in p, where the function in p is e raised to the power of p, negative e raised to the power of p, and px remains the same. So since this is the form of the Clairaut equation, we can easily substitute a constant for p to get our answer. So now y becomes cx minus e raised to the power of c. And this is going to give us the solution of the differential equation. So this is pretty straightforward. So we've come to the end of this video, and at this point we've talked about all the 4 case studies for equations of first order and higher degree. So go through the videos and get a lot of practice questions in, and these concepts are very straightforward. Thank you very much for watching this video. See you in the next video.